Well, hello everyone, and welcome to the next in our series of Dare Hub webinars. I'm Dr. Sam Cocking. I'm a postdoctoral researcher at the University of Cambridge, working as part of Dare, which is the UK's national research hub for decarbonised, adaptable and resilient transport infrastructures. Dare brings together academic researchers and UK transport stakeholders, including national and local governments, transport infrastructure owners and operators such as Network Rail and National Highways and their supply chains and partners, to explore viable pathways towards a resilient net zero transport system. The Dare Hub is funded by UKRI, EPSRC and the Department for Transport, and involves a collaborative team of researchers from Newcastle, Glasgow, Heriot-Watt, Cambridge and Anglia Ruskin universities. In today's webinar, we're going to be talking about deterioration. Like many mature economies, the UK has a lot of aging infrastructure, and it's been estimated that we add only 0.5% to the capital value of our built environment through new construction each year. It's clear that the vast majority of our future infrastructure already exists today, and we're going to need it to continue to perform for many years to come. But at the same time, transport infrastructure is vulnerable to deterioration under cyclic vehicle or weather-driven loading, and we face challenges in quantifying historic and ongoing deterioration. It's critical that we need to understand this real structural capacity, though, so that we can predict future performance and optimize our asset management strategies. In particular, we need this knowledge of current behavior and deterioration so that we can estimate the added impacts we may face in the future due to climate change. But luckily, with modern approaches ranging from structural health monitoring through advanced computational modeling to data-driven strategies, including machine learning, it's increasingly possible to study these complex deterioration processes despite these challenging uncertainties. Now let me introduce our first speaker for today. Dr. Chris Power is a technical director in the civils asset management team at Mott MacDonald. He is an engineering geologist with over 25 years of experience in the management of earthworks and drainage assets, and he's worked extensively for major transportation network operators in the UK and overseas. He has a particular interest in furthering best practice through collaborative research and was the chair of the Industry Impact Group for the Multi-University Achilles Research Programme, and he's a member of the Scientific Advisory Committee of the British Geological Survey. So with that, thank you very much, Chris.
Great, thanks, Sam. Thanks for that introduction. Hello, everybody. Hopefully you can see my screen. So yes, I'm going to be talking about transportation earthworks today and a body of work that I've been involved with for quite a number of years. So just to help orientate everybody to start with, just an understanding of transportation earthworks. So pretty much everybody that works in anything to do with asset management or managing assets says that their earthwork is the most, that their asset group is the most important one. I appreciate that, but I'm going to argue that earthworks is one of the key ones because it underpins all transportation networks. So going back even to pre-railways into the canal age, smoothing out the landscape to allow transport networks to pass through the landscape has required earthworks. So whether that's large embankments taking you over valleys, as you can see on the left-hand side here from a railway, or on the right-hand side, getting our transport networks through the landscaping cuttings. We've been building earthworks for a very, very long time. And in our part of the world, some of the portfolios of earthworks that we're dealing with are really quite sizable. So I've been involved with mostly working with Network Rail and National Highways and its predecessors for many, many years. If we look at the railway network of Great Britain that Network Rail has responsibility for, it's a network that's nearly 10,000 miles in length. And by the definition of earthworks that Network Rail uses, there's nearly 190,000 earthworks that exist around that network. And I'm sure that you can imagine the size of the network and the coverage that it has means that encompasses a large number of different geological material types that the network passes through. For National Highways, who have responsibility for the strategic road network of England, a smaller network, 4,400 miles, but a decent number of geotechnical assets that need to be dealt with as well. So nearly 50,000 geotechnical assets that National Highways has responsibility for. And one of the issues that network owners have is that depending on which owner you are, these earthworks are quite aged. They've been around for quite a considerable number of years. So this chart here from a presentation that Tim Spink did in 2019, shows the kind of the percentage of network constructed in a given year for both the rail network that Network Rail has and the motorway network of National England, and going into HS1 for the link down to the Channel Tunnel. So the main body of earthworks construction that Network Rail and the rail network had was in the 1820s to 1860s. So they're pushing 200 years old, some of these earthworks now that are on the rail network. Obviously, the motorway network, somewhat younger, sort of built from the late 50s with a main drive through to the 70s and another peak in the 1990s. But even that, they're starting to show their age now. We're starting to look at things that are sort of pushing 70 years old, some parts of the network. And the pictures around the outside here obviously show one of the challenges that this age of these networks bring us is the change in the construction techniques that were applied when they were built. So on the left-hand side, you can see the relatively rudimentary way that earthworks were constructed by the Victorians. Lots of animal and human power to move things around. Embankments, just materials tipped off the edge and self-compacting, or compacting by the weight of horses alone often. By the time that we're building the motorway network, we've got an understanding of soil and rock mechanics, more modern plants available. So materials are being better selected and better constructed and placed. And then when you look at the more modern networks, HS1 in this example, but obviously HS2 being built at the moment, we're in a much more advanced age of how we go about constructing them. But they are aging, and conceptually, one way to look at deterioration is to look at it from this kind of bathtub type curve, albeit I always find it a bit odd that the bathtub's upside down, but you get the idea. So this is from a paper that's been reused and kind of redrawn in multiple ways. But in this representation, you can see against asset age, if you look at that being your x-axis increasing to the right, and if you look at performance of your assets being from low to high on the left-hand side, this bathtub will typically show that you have a period of poor performance as an asset beds in, and you definitely can see that in earthworks that are being constructed. You might then have a decent long period of reliable operation, and then as deterioration starts to occur, you can see some degeneration to an unreliable state and potentially even asset failure. And these curves will obviously vary in their shape and their gradients depending on all sorts of factors. But typically, if you were to conceptualize it, perhaps the motorway network that National Highways oversees is in a reliable and starting to see some degeneration. Network Rail's asset somewhat older, perhaps seeing more generation and unreliability. And new assets will hopefully be at the start of their journey and may bed in, but hopefully should be into a reliable period. So how does that deterioration manifest itself? There are all sorts of mechanisms by which earthworks can deteriorate. And I've listed a few of them here. When you're building a cutting in the natural ground, typically the water level in that cutting, perhaps not at the moment, but will typically be quite high, perhaps near the ground surface. When you dig a cutting into that, you induce negative pore water pressures. That can take some time to equilibrate itself, particularly in low permeability materials. That can drive failures, and you can quite often see early life failures due to that mechanism. Weathering, typically thought of as a geological process over millennia or millions of years, absolutely does happen in engineering time. Observations made of clay cuttings that were kind of cut in the 80s and 90s have shown that they are weathering within sort of in decadal time. Wetting and drying of particularly clay materials is an interesting area, and these charts on the right can show when you monitor a slope through wet winters and dry summers, how shrinking and swelling of those slopes can result in horizontal and downslope displacements of those slopes as they wet and dry through those periods. There's also erosion of the surface of slopes due to overland water flows. We're starting to see more and more of that happening. Vegetation obviously grows on quite a lot of earthwork slopes. That can have positive impacts, but it can also have negative impacts on how the assets deteriorate. Freeze thaw, particularly of rock slopes, where water can get into the joints of slopes. It freezes and expands, and that can force materials out. And animal burrowing is also quite a significant problem, particularly in soft geological materials. One thing that stands out when you think about all of these mechanisms of materials is that quite a number of them will be impacted by the weather. And even more so, it's particularly the water within the weather, so rainfall, snow, etc., and the inverse of when it dries out, that causes quite a lot of these mechanisms of deterioration. And that can then manifest itself in various ways. Most asset owners will consider that they have either defects or you get past that point to where you start seeing failures. And I could list all sorts of photographs in here, so I've just chosen a few. On the left-hand side, in a rail network, you might start seeing deflection in your rails. You can see a dip in the rail there, where there might be some movement occurring in an earthwork slope. You may start seeing large cracks, as you can see on the bottom left on the motorway network, which may be due to shrinking and swelling of materials. It may be tension cracks due to slopes starting to move down slope. Typically, asset owners will be looking to inspect their assets to look for those incipient type failures to try and nip them in the bud. But sometimes you can't get there, and it goes to the point where assets fail. And there are many examples that you can show across both rail and motorway networks where these failures have occurred. And it can be as dramatic as rails being left dangling in the air, or almost a sort of a delta forming as water's washing out on the bottom left. Or it could be large slope failures on a cutting, as you can see on the bottom right on the motorway network, which you may think can sort of keep itself within the slope in a cutting example. But in that case, it was starting to push up the hard shoulder of that road at the bottom there. And that road at the bottom there is the M25 in its southern portion. So the impact that that could have had if that had carried on was quite significant. Now, one obvious thing, I've mentioned weather relationships. You very clearly see relationships between rainfall and the number of failures that you see. So this is from Network Rail's work. So on the left-hand side, you can see monthly average rainfall in that top chart, and then the number of monthly failures in the bottom. And you can see that the peaks in failures can correspond very strongly where we're seeing significant rainfall events. The charts on the right are interesting, where the seasonal rainfall is split up to represent where you're seeing in excess of the normal amount of rainfall relative to the number of earthwork failures that you see. And typically, in my earlier career, it was the winter that you worried about. So it was mostly more rainfall in the winter, more failures. What you're starting to see more and more, particularly on the right-hand chart where it's been normalized to long-term averages, is the pale green dots, where we're starting to see huge amounts of rainfall in the summer, causing large amounts of earthwork failures. So how do we look at deterioration and trying to predict it and model it? So a way that it's been done by many asset owners is to break down the condition state of your assets into some kind of classification. So in this case, giving them a classification from A to E, where assets are in best condition through to their worst condition in E, by looking at the number of defects that you see within them, and also looking at how many failures that you get. And then measuring from your observed records of inspecting them, what's your likelihood of moving from one condition state to another in a given amount of time, and then modeling that in a Markov chain methodology, and then looking to see how that could be wound forward into the future to produce the types of charts that you can see on the right-hand side. However, one of the problems with deterioration predictions like this, when you're looking back into the past, is that and then projecting it into the future, is that you're inherently assuming that the same drivers are going to be occurring in the future as have been in the past. And we know that external drivers, such as climate change and traffic loading, are changing. So it's not necessarily a valid way, useful as a benchmark and a baseline, but not much better than that. But you can do better. So some excellent work was done as part of a research program called Achilles that ran for a number of years, which really got into the nuts and bolts of modeling how changing weather into a model can drive deterioration that we see in assets. So these charts on the left-hand side at the top shows a current climate, which was then the current climate wound forward into the future to derive a weather trace, which is then fed into earthwork stability models. And the time on the x-axis, but a factor of safety on the left-hand side on the y-axis, and at a factor of safety of 1. Below that, you're looking at an earthwork slope failing. And if you take a current climate and wind it forward in the top chart, you see that our asset slopes can exist for hundreds of years into the future. When you model that with a plausible climate change projection in the bottom chart, we start seeing way faster deterioration and far shorter times to failure. So some work was being done by National Highways to take those results and push that into the deterioration model to give some kind of accelerated climate change projections in those blue and orange bands over the baseline climate prediction, where we can start seeing more expected annual failures due to this type of deterioration methodologies. We've also, work's also been done as part of Achilles to look at what might be the impact of future climate for new slopes. So this was looking at slopes in a intermediate plasticity clay material, such as the Mercia mudstone. And on the left-hand side is taking the typical types of slope angles that we would cut our slopes in. So 1 in 2.5 at the top, 1 in 3 in the middle, and 1 in 3.5 at the bottom for slopes in different heights. And typically, earthworks designers would be asked to design for 120-year design life. And you could say that if climate carried on as it was for now, you might expect that with these typical earthwork slope angles, we might get that 120 years. But if you start modeling plausible future climate change, we start seeing that these slopes that we're quite comfortable designing at the moment might not make it out to that 120 years, maybe failing before that. So I don't think we can be relying on our business as usual engineering methods for dealing with things in a changing climate. We also need to recognize that in earthworks, it's not just about rain, it's not just about water. So we're starting to see projections of way increased wildfire risk. That removes vegetation. That vegetation can often be beneficial for the stability of slopes. And it's not just a potential problem. That in 2022 near the A2 in Dartford, you can see there in that picture, a wildfire was pretty close to an open motorway. These types of things are actually manifesting themselves already, and we need to be thinking about that. We also need to think about more than just failure. Shrinking and swelling of clay slopes is an important area, and National Highways already deal with this, have already got hazard ratings for their network held in their GDMS system, and based on some of the products that the British Geological Survey produce. And going back to GDMS and asset systems, one of the things that we can do to manage risks is to actually understand our assets and understand the condition state that they're in. We're very, very fortunate in our neck of the world to have two absolute exemplar systems for holding that asset information system. I genuinely think that these are the best in the world. So National Highways has Geotechnical and Drainage Management Service, which has been holding information on their assets for over 20 years. And Network Rail have an earthworks database, which holds similar information and is very advanced in even bringing in weather forecast information so that the management of earthworks can be included within that. We also need to break out of the silos that we work in. We need to stop thinking about us working just on earthworks, just on structures, just on track or pavement. We need to recognize that there are interrelationships between assets, and particularly for earthworks, drainage and the management of water is a key thing that we need to be breaking down these silos more and more. And that was recognized in the report that was done by Professor Lord Mayor after the Carmont tragedy in 2020, which very clearly recognizes that the effective control of water and understanding of the maintenance of drainage assets is absolutely fundamental to understanding how we operate a safe railway network, and the same could apply to any kind of transportation network. We also need to more and more make use of technology. It's getting harder and harder to inspect assets physically. It's a potentially dangerous environment. We want to keep people away from those slopes as much as we possibly can. So more and more asset owners are looking at ways of observing their assets without having to physically go and see them. That might mean, for example, on the left, Network Rail are deploying slope monitoring all over their slopes around the country. These are examples from Scotland. And various people are looking at things like satellite INSAR to look for movements of their slopes from space. And that brings its challenges because that generates huge amounts of data for which different ways consuming and making information out of that data will need to be looked at. But it's definitely an area that we're going to be more and more taking advantage of. And the final slide that I've got really is thinking about, well, ultimately, what can we do to our earthworks in a changing climate? And one of the issues that we have around changing climate is that there's uncertainty in the way that the climates will change, and we can deal with that insofar as we can. But there really is very, very little science around how that changing climate will actually impact on earthworks. The Achilles project really stands out as being one example of where we've got some decent science. But in any of the other ways that climate might impact on earthworks, we really are very much in an engineering judgment space at the moment, and more work needs to be done. But one thing that we can be doing is thinking about when we build assets or we intervene on assets is just make them adaptable. So take the concepts of adaptation pathways and build assets such as this one in a really good paper from Thompson John that was built in the A40 in the Brecon Beacons. Build assets that we can get to. If we need to clean the drains and keep the drains working, we can get to those drains really easily. If we need to make ditches bigger, we can at least get at the assets so that we can adapt them into the future. So we're going to need to have some of that adaptability in the way that we do things going forward into the future. Thank you very much. If we've got any immediate questions, I think we'll take them now.
Thank you, Chris, for that great presentation. If anyone has any questions, would they like to unmute and go ahead and ask? Or put them in the chat if they prefer.
I have a quick question for Chris, may I? Just that last example there, that looked very much like what you would call a grey solution. Have you looked at, or are you planning to talk more about nature-based solutions as well for stabilizing slopes?
Yeah, no, that's a really good question. That it's I would say it's definitely something that everybody's got the will to do, but it hasn't necessarily caught itself up into the sort of mainstream way that people would deal with it as being a solution. So the various asset owners have definitely got the start of dealing with those types of things, but it's very much an area where there's a lot of opportunity to be dealing with it. Network Rail and National Highways are both starting to get more and more interested in the whole catchment consideration around their networks, so management of water in their catchments and use of nature-based solution to kind of retard the water within catchments is something that more and more is being picked up. So it's an area I'm quite passionate about doing more about, but there's definitely there's more work to be done in that space for sure.
Okay, thanks.
Yeah, good question. Thanks.
Yeah, so we've got a question from Josh in the chat who says, could Chris expand on or share specifics of the example presented in the last slide? So I guess that's following on again from the question we just had.
I mean, that's the one example that I brought out because it's one that I'm aware of because it was kind of done within Mott MacDonald. I mean, that stood out to me. I'm sorry, I'll share my screen again now because just in case anybody didn't get the link in time when I was presenting it. That stood out to me as being a really good example of where people had actually done some work on properly thinking about how they could adapt things. I've not got too many other examples, which perhaps tells me something about this is an area where we need to be doing more. If I'm honest about it, quite often in the design of new assets, people start with good intentions on making things adaptable and making sure that we can access them. And as projects go on and costs might increase, things like this quite often get cut out. And a longer term thinking about how we manage not just our earthworks, but all of our assets, and thinking beyond the point of just the construction costs and starting to think about the total cost of ownership costs into the operational phase is something we really, really do need to get better at. So, I'd love to have more examples, but that's the one I can pick up.
That's good. We've got another question in the chat from M. Pandy who asks, are you using non-homogeneous Markov chains to account for non-stationary effects of climate change?
Yes. I can answer that one quite quickly. Yeah, it's a non-homogeneous Markov chain modeling method that we use, yeah.
Great. Any other question? Oh, Pete's got his hand up. Pete, do you want to ask?
Hey Chris, it was just sort of a comment/question about vegetation, really. Um, it's a difficult one, isn't it? Because it can be both beneficial and negative. It can, sort of accelerate shrink swell, but at the same time improve slope stability. Um, do you think we as engineers get enough or even any training to sort of try and understand vegetation and how it's best dealt with in a sort of engineering context? Because I'm not sure I've ever really had any. It's sort of all stuff I've learned accidentally while doing any other things. I wondered if you had any views on that.
Yeah, no, that's a really good question, Pete. And yeah, thanks. It's worth pointing out that I've used a number of your charts in the things that I've done here, and it's been absolutely pivotal to a lot of the work that we've done. But you're absolutely right, Pete. So Network Rail have got an earthwork management of vegetation on earthwork slopes standard within their module. So there's definitely a start in the way that things are done there. But I would say if I was looking at a typical design project where people are thinking about the planting of vegetation on new assets that have been built, it is not geotechnical stability thoughts that's at the forefront of people's mind when that's done. It's about maintainability, it's about landscaping, it's about aesthetic views of things. If you look at the way that sometimes Network Rail can manage its vegetation, it will be about leaf fall onto the track, which is absolutely important. You've got the operation of the trains being a dominant thing, but sometimes trains will be removed, which will remove one risk but cause a bigger risk on the earthworks. So I think you're absolutely right, Pete. We're not considering enough of what's going on, and I certainly don't think we're doing too much to think about how climate change will change the types of vegetation that can survive on earthwork slopes and how that might change in the future. So yeah, again, another area where there's more work to be done. Absolutely.
Right. I think I have time for just one more question before we move to the next speaker. I see Phil's got his hand up.
Yeah, well, first of all, Chris, fantastic presentation, really insightful. Your point about the nature-based solutions and looking at new plants and the like that can help with that. I think that's absolutely critical because we're seeing so much being published about some of the traditional fauna, which is not growing as well and performing as well. What's needed to take that forward? I mean, is it things that individual companies are looking at, or do you need? Is there a need for the industry as a whole to really come up with solutions and standards and things that they feel will make a difference in the future?
Yeah, it's a good question. So I mean, I can answer it from a perspective of the company that I work in. So within Mott MacDonald, we've got specialists now who in working in nature-based solutions to schemes. There's guidance out there. There's Syria have got documentation that's worked on looked into nature-based solutions and making the best of it. The key thing to me is getting the message across. Getting quite a lot of designers will be part of they'll be used to designing things in a certain way, and they'll be within a team where they've things have always been designed in this way, and that gets passed down the team. And I think we've got to break into that and get people to realize there is another way of doing these things. And I think companies can do what we can internally to get that done. Our younger designers are itching to find more sustainable ways of doing things, and we need to really sort of harness that enthusiasm and get people to sort of work more and more on those types of things. But client organizations also need to drive it from their end as well, is make it part of their requirements for that to be considered. Don't just put it onto the supply chain to kind of bring those things forward, but make it part of the way that schemes are set out from the start. We've got to come at it from multiple viewpoints, and just enthusiasts need to be out there, don't they, advocating for it.
Sam, is it okay if I do ask a very quick supplementary question? And that is, are universities helping? Are universities delivering graduates to you that are aware of these new solutions and are helping you renew your thinking in this space? Or is it something that we're not doing as well as we should?
Yeah, that's a good question. Yeah.
It is.
Yeah, that is a good question. I mean, I'm just thinking about some of that. So I mean, we've got someone that started in our team relatively recently. He was part of the Newcastle, came from Newcastle and was part of the Achilles project. And I'd have to ask her. I'd have to ask that question. You know, when we've certainly got we've got a whole team of people who are working on nature-based solutions, and you know they will be. You know, we're recruiting people into that team who are relatively well informed. But it's really about people that are out there actually being part of design teams that it would be great if they kind of knew more about it. It's a really good question. It's a good thing to mull on that, I think. Yeah.
Great. A few other questions have come into the chat, but I think we will need to move on to the second speaker now, and there will be another opportunity for questions after the second speaker, so we can come back to those then. Great. Our second speaker is Dr. Zhou Wang. Dr. Wang is currently a Marie Curie Fellow at the University of Cambridge, serving as the core researcher on a project on smart materials for sustainable road infrastructure. That project's funded by the European Commission. Prior to this position at Cambridge, Dr. Wang earned both a bachelor's degree in civil engineering and a doctorate from the National University of Singapore, combining a combination of numerical simulation, machine learning, data-driven methods, and stochastic optimization. His research aims to combine knowledge of material spatial heterogeneity with subsurface conditions to inform systems-level simulations of interactions between geosystems, humans, and the environment, and to use field observations to calibrate numerical and data-driven models for knowledge discovery. His research has led to 30 journal articles, and in addition to contributing to research initiatives funded by the European Commission and the National Research Foundation of Singapore, Dr. Wang's research has led to products employed by government and industry sectors for ongoing infrastructure projects. Great. Thank you, Zhou.
Yep. All right. Okay. Can you all see my screen? Share screen? Yeah. Hello, everybody. I'm Zhou from University of Cambridge. I'm currently a Marie Curie Fellow of Cambridge. So today I'm just going to share a little about my research, my fellowship on the very topic of data storytelling of road deterioration. Right. So yeah, we all know that road infrastructure are very important, and they're responsible for the transportation of goods and people. And then if something undesirable happen for the road infrastructures, you know, we can end up with very significant, as in catastrophe. I would say catastrophe, but the consequence can be quite significant. So this has really led to the Cambridge Digital Roads of the Future project. And this particular project supports two big grants, Digital Roads and Future Roads, which are jointly sponsored by EPSRC, the Marie Curie Council, Costain, National Highways, and multiple other industry partners in the UK. And this whole program really housed more than 50 researchers, and I'm actually one of them, working on a very specific aspect of the overall road infrastructures in the UK. So this particular project actually consists of multiple themes that range from digital twins, data science, automation, and robotics, and smart materials, and all centers on the very topic of sustainability. So as for my research in this plan is really at the intersection of smart materials and data science. So I'm actually working on the topic of two themes in this very big research projects. So I guess my presentation is a little bit of academic. So I start with really presenting my research vision, which is, I try to summarize my vision in one single sentence. It's a knowledge-guided data storytelling for understanding our roads. So essentially, my approach consists of three different components. And the first component is about data-driven analysis, where actually I collected national scale data and designed data-driven approaches to forecast pavement or the road's performance based on a certain historical data, historical performance data, or the traffic or the climate or the environment factors, I can then leverage machine learning to really draw insights and learn from all these historical data. And based on these understandings, the machine learning model can really forecast the future road or pavement performance, whether it's about cracks or it's a general performance indicator like the International Roughness Index or the rotting depths. But given the criticism of data-driven analysis for being a black box and lacks of physics-based knowledge, the second component of my proposal or my research really tap into the numerical simulation model to really capture the physics-based relationship between the material properties or the material behavior and the overall response of the pavement system under the real traffic dynamic loading. But at the same time, in order to capture the real in-situ behavior, then also tap into the monitoring techniques. And specifically, I focus on this comparatively new technology. Of course, it's compared to the falling weight deflectometer. This traffic speed deflectometer is the main monitoring techniques that I focus in my research. So if you really combine the simulation and the monitoring component in a model calibration framework, it is actually possible to calibrate the model in a way that the model outputs really match what has been measured by the traffic speed deflectometer. And in the sense, the calibrated model can act as I would say probably a digital twin, if you want to put it in a more fancy term, a digital twin framework. And then we can use the calibrated model to simulate the pavement response under various loading conditions. And this then allow us to also understand what's going to happen in the future for the specific road of our interest. So in this case, you can tell that I can actually obtain the road performance forecast like from two different angles, one from the data perspective and another from the sensor the monitoring perspective. And of course, the ultimate goal and what I am currently working on is really to harmonize these two components to really put them together to formulate what I call the knowledge-guided data storytelling for really understanding our roads. So today I'm just going to talk a little bit about this component, the model calibration component. So first of all, for the traffic speed deflectometer is a probably, as I say, comparatively new technology, of course, compared to falling weight deflectometer. Essentially, it is just a measuring truck equipped with a number of sensors. Next, for example, this is a laser Doppler velocimeter that actually measure the pavement deformation or response as the measuring truck is moving, at the traffic speed. That's why it's called traffic speed deflectometer. So the actual data that we can monitor data we can get from the TISD device is actually the corresponds to the pavement deformation, right? The actual deformation, if you really take the first derivative of the deformation, we get the deflection slope. But regardless of the type of data, a very common way of using the data is to couple with the physics-based simulation model, numerical model, or in the simplest sense, an empirical model that describe the relationship between pavement response and the material properties, and in the back calculation framework. And in this way, we can actually back calculate the material properties. For example, in the pavement system, the modulus of the three different layers in the standard pavement systems, right? So this value then can be considered as the in-situ value of the material properties, which can then be used to carry out quite a lot of downstream tasks for understanding the pavement response for future scenarios. So my work really focused on developing techniques to better interpret the TSD data in the overall framework of back calculation. So for the back calculation, we actually need the collective efforts from a number of components. And first of all, it's a physics-based model. We need a high fidelity model that really captures the physics relationship between the material properties and the actual pavement response under the external loading conditions. So in this particular case, we use this pave move developed in-house to really simulate the pavement deformation under the TSD dynamic loading. So with this high fidelity simulation model, I then use the Bayesian updating as the very techniques to calibrate these the simulation model based on whatever measurement data collected on site. And the advantage of Bayesian updating is that it transforms the conventional deterministic back calculation framework into a probabilistic context, which then allow us to really explicitly consider a number of uncertainties in the system, say measurement uncertainties, or even the uncertainty that exists in the material properties. But however, in order to transform this back calculation exercise into real-time or near real-time that align with the data collection nature of the TSD device, machine learning is a good tool that can speed up or accelerate the whole back calculation. So in this case, I've developed machine learning surrogates to, at the same time, capture the high fidelity simulation from the original physics-based model, at the same time reduce the computational resources that we need. As you can see from here, from 2 minutes per simulation to about 0.01 second per simulation. So these three components collectively then carry out this back calculation framework to interpret the TSD data for us to really understand the individual material properties. So I've just tried to test this whole framework using some real data. Unfortunately, this is not in the data from the UK, but these are the two very classic case studies that people use to test whatever framework or techniques developed for interpreting TSD measurement data. It's one in Denmark, one in Norway. So I try to compare my solutions with two others. To make it simple, I just call it basic version and some advanced version. And this is what my approach will provide. So let's really start from the first key parameter, which is the modulus of the surface layer, right? So in this figure, actually, we can see a lot of information, including the engineer's initial estimation and the histogram representing the back calculated material properties. At the same time, I also co-plotted number of reference values to provide a way to sort of semi-validate the results that I can get from the back calculation framework. So probably you can tell from this, from the dual perspective of accuracy and uncertainty quantification, at least my solutions provides a much better, narrower histogram representing improved uncertainty quantification compared to the very basic version of this back calculation framework, right? Also, in terms of accuracy, I see a reasonable, agreement between whatever results I obtained with the reference results provided in this particular case study. Similarly, for the second key parameter on the modulus of the base layer, we have a very similar observation where my solution provides a much better uncertainty quantification. And the last parameter is the modulus of the subgrade layer. So we also see a pretty promising performance of my solution that really balance out the uncertainty quantification as well as accuracy compared to the advanced and basic version of this back calculation implementation. So although I have many other results to show, given the time, this is the results. I just want to highlight the kind of improved results that I can really provide based on what the methodology or the framework I can produce in my research. So similarly, for the second case study on Norway. I just quickly go through it so we can actually see very consistent observations, as in the case study in Denmark, that my solution provides a better interpretation of TSD measurement data for understanding the in-situ material parameter values. So what I really want to highlight is that to really make or benefit the industry, I'm now actually developing a standalone user interface that actually helps the whatever algorithms or framework I develop in my research, so that industry can directly use this software to carry out or interpret TSD data. So I provide the user with a number of functions to choose different material constitutive models, to input parameters, and then most importantly, I offer the flexibility to configure different sensor locations, because the TSD device, different companies may have different specification. So I gave the user the flexibility to really define the number of sensors and the location of these sensors, so that whatever analysis can be based on this particular sensor configuration, right? So the machine learning model based on the high fidelity simulation model has been pre-programmed into the software, which allow us to really generate or understand the pavement deformation. So as comes to the back calculation, users can upload the TSD data from Excel spreadsheet, and I also provide certain algorithms, which exactly the one that I try to advocate to improve how we interpret TSD data for understanding the in-situ pavement material properties, right? So in this way, engineers can also incorporate their initial engineering estimation to really facilitate the back calculation and choose between the conventional deterministic or probabilistic approach with some inputs on the uncertainty that exists in the systems. And then the software can automatically sample the posterior distribution of the material properties based on whatever measurement data we upload to the systems, right? And then user can really can also monitor the this whole process to evaluate whether the calculation is whatever results are valid. So in this case, we can really sample a probabilistic distribution of the material properties, which give us additional information other than the mean or the average behavior, but also the standard deviation or the uncertainty rate information. So this is what I have developed so far. The work is still ongoing. It will certainly include additional features, functions based on the outputs of my research. So the eventual way to really combine the two data arms, the two arms, right? Conventionally, I've implemented the conventional machine learning strategy to really consider some input data related to traffic, environment, and historical data performance. And through machine learning, we can provide a prediction of forecast of the road performance, say crack length, rutting depth, or international roughness index into the future, right? The future conditions. But again, as people have been criticizing about pure data-driven analysis for being, a black box, and this really presents the opportunity to really incorporate the second arm of my work on the understanding of the in-situ material properties from using simulation model as well as in-situ measurement data to provide this additional information, which is based on the physics-based knowledge into the overall implementation, so that the second arm can really regularize help with the pure data arm to eventually, hopefully, improve the overall forecast of pavement performance. And this will allow us to really establish a deterioration mapping that represents the different rate of deterioration at least in the regional scales. So the takeaway and some thoughts about this work is that TSD is I'll say a pretty promising techniques that actually can capture the response of pavements of the roads under the really realistic moving loading conditions. So in this case, I provided a machine learning accelerator Bayesian updating framework to improve how we can interpret TSD data from both the accuracy and uncertainty quantification perspective, right? So I'm trying to advocate for this probabilistic approach over the conventional residual minimization approach in interpreting TSD data for understanding road performance. So last, I just want to provide some thoughts that I have, as I go to conference and talk to people. So based on what I observe is that if you really, on the very topic of this TSD in terms of research efforts, I see a kind of a significant amount of work going on in the US compared to the UK. But what is actually quite interesting is that I know that the TSD data has already been integrated into the pavement management system in the UK, where in contrast in the US, even though there are a lot of research work going on, TSD data, I may be wrong, but quite a lot of my friends in the US told me TSD data has not really been integrated in the US PAM systems. So TSD was actually first developed in Europe, Sweden, Norway, and Denmark, and now I see a significant research work in the US. So I have also tried to communicate with the industry, see why TSD is not really widely adopted in the UK, is that there have been some reports of discrepancies between the results of the interpretation of TSD and the conventional falling weight deflectometer. So, but I'm confident that by providing advanced interpretation techniques like the Bayesian framework, we're able to really provide improved interpretation results using TSD data, which I think paved the way for its wide adoption, at least in the UK. So this is what I would like to share today. And yeah, now I'm open to questions. Thank you.
Thank you very much, Zhou, for that great presentation.
Yeah.
Do we have any questions for Zhou, either in the chat or if anyone wants to unmute and ask?
Hi, it's Piers Treach here from Network Rail. Could we go back to there was a slide that showed the three different methods, or the results of the three different methods. Could you go back to that a moment and just talk me through again sort of the reasoning behind why the proposed technique is giving much better results? Because I know you explained it, but it was on screen fairly briefly. So
okay, I'm trying to provide my argument from two perspective. One is the accuracy, the other is uncertainty reduction or uncertainty quantification. So from the uncertainty reduction perspective, I'm just trying to examine the standard deviation or the width of the histograms. And if the histogram is wide, basically it represents the results is associated with very significant uncertainty because the variations are significant. That basically means that we don't really extract much information from the actual measurement data. For example, you can see from here, right? This black line represents the initial engineering estimation, right? They just provide an engineering estimation. But if you can really see the standard deviation between the engineer's estimation and the back calculation results, in this case, we actually don't see much difference. So that means we didn't really get additional new information from the measurement data compared to our initial estimation. Where in contrast, from here, we can see that the distribution is narrower, meaning that we extract certain amount of information from the measurement data that help us better understand the material properties to reduce the variations.
But the way the figures will be used, though, as they go through into the modeling, are you using a distribution or are you using a point value? Because if if it's a point value, then the standard deviations being displayed surely are less, they're less interesting. Whereas if it's a distribution that you're using and you're getting a tighter distribution that you're then modeling from, I can understand that. Because I mean, simplistically, you know, if you've got an engineering view that's giving you, you know, a spot value that you're then assuming a normal distribution from, if that spot value actually correlates really well with what's being measured anyway, then the fact that, you know, you're calculating a tight distribution isn't that's not really the comparison, is it?
I want to say this is a spot value because as you can try to think of the nature of the data collection, is that the truck is actually moving on the road, and you can say that the material property, whatever value actually represents a sort of not necessarily at a single very localized location, but actually over a certain area of the pavement. Because if you think of the load acting on the road, it actually is a whole area of pavement that may be deformed under the loading. So you can say that this represents an aggregated kind of information over a certain range of the pavements. So I'm not sure, but
yeah, okay, but then I don't. But so I get that, but then I don't understand why a tighter distribution is necessarily better then. Because if you're saying the distribution is necessary to represent the fact that, you know, you've got a big area of road, so depending on which bit of it you're on, you're going to end up with a slightly different value. Then it doesn't follow to me that having a tight distribution necessarily means it's better. I mean, it may well be, but I'm not sure that necessarily follows. So I'm just trying to understand. I'm just really trying to understand kind of how you're gaining confidence that this is definitely an improvement in technique.
Because in terms of let's say we have a distribution of the material properties. This, as in standard deviation, basically represents the variation, the possible variability of the material properties, right? So let's say we have a wider distribution with a higher standard deviation, meaning that the variation is really very significant. Then if we can, so the goal is to really to reduce this understanding, reduce the uncertain knowledge about the material properties. And this essentially translates into a narrow distribution. So the narrow the distribution, as in the more certain we are about the material properties. Yeah, I'm not sure whether that explains.
No, I suspect you're right. I'm just probably not really understanding exactly how the values then translate through. Have you got a paper that you've published recently on this?
Most of the work are currently under review. So yeah, hopefully it can be published soon.
Sure. Okay. Well, I'll look out.
Yeah. Thank you. Yeah.
Really good presentation. Really interesting. Thank you.
Thank you. Yeah.
Great. I might just ask a quick question following on from that. One thing I was a little unclear on is when you have those sort of histograms that show the distribution, that's corresponding presumably to your estimate of the sort of as measured state or as modeled state of the road. Is that right? So you might pick up, for example, if you had a very tight distribution around a certain value, that suggests that the material is all sort of relatively homogeneous in terms of its material properties. So maybe if there's been some deterioration, it's relatively uniform. Versus if it was a very wide distribution, would that mean it's actually there's a lot of heterogeneity in the material? Some of it's deteriorated more, some less. Could you comment a bit on that, perhaps?
Right now, I don't think there is a direct relationship between this and what you are thinking. The heterogeneity or the homogeneity. Yeah. I don't think there's a very clear direction. So I think the histogram mainly reflects our knowledge about the material properties, right? So initially we are very uncertain about the plausible value of these material properties. That's why probably we gave a very large uncertainty region, say 30% coefficient of variation. But then if we can, if we use the monitoring data and through some kind of interpretation, we know better the material properties, right? That's essentially translate into a reduction in the uncertainty, the distribution, because we collected the monitoring data and interpreted it, which help us better understand. Possibly, it can vary from 1 to 10, but initially without any additional information, based on our engineering knowledge, it can vary from 1 to 20.
Mhm.
Yeah, the information that helps reduce our uncertainty information. As for to really understand the heterogeneity or the homogeneity of the material, this is a very interesting topic. Actually, and because of these very questions, it's already kickstarted. It's sort of a side project we're currently working on. It's not really part of my fellowship, but actually we obtained quite a number of core samples from M25, if you remember, right? So we are planning to kind of CT scan this material so that the CT scan can really uncover the kind of the very detailed distribution of the different materials in the core samples. This actually reflects the origin of the heterogeneity or homogeneity. So this can actually help us really understand or characterize the heterogeneity of the materials. Yeah.
That's great. Thank you.
Mm.
I see you've got, I'm just looking at the chat for other questions. I see there's one from Mpandi again, who asks, are you using the WinBugs package for MCMC simulations for your Bayesian updating?
Okay. I'm not using this package because as you can tell, this problem is pretty simple. It consists of only 3 parameters. So I'm just using the very conventional Markov-Chain Monte Carlo with Metropolis hissing. So I don't need to tap any existing package. I can just write it myself. It just only like 100 or less than 100 lines of codes. And based on my observation, it's already sufficient to handle a problem of this level of complexity. But if we have many other additional parameters, say if we need to handle more than 10, 20, then probably we need to tap into those more advanced sampling techniques to sample the posterior distributions.
Great, thank you.
Mm.
Any other questions for Zhou? I had one other question around the materials of the road surfaces you're looking at. So is your model trained for particular pavement materials, or do you have a database of measurements that covers sort of different pavement materials and compositions?
You mean the machine learning part?
Yes, that's right.
Yes, I try to train the machine model in a more general sense. In the sense, I actually compile a quite big database of quite a long list of material properties, and then try to search for the minimum and maximum possible range of this material from the literature and kind of observe on the road. And then I build a huge database to train this one single machine learning model that is believed to be able to handle this big parameter space. Yeah.
Great.
Mm.
Okay. Conscious of time, so I guess last opportunity for any questions. But if not, then I'll just go ahead and thank Zhou again and thank Chris, although I think Chris has had to jump onto another call. But thank you to both of our great speakers for the presentations today, and thank you for giving up your lunchtime to come and attend this webinar. We hope you found it interesting.